All right, so it looks like I've got Zoom going and all that kind of jazz. Actually, before we do this, let me upload those files to Moodle just in case. So my courses.
Is there a certain name that you want this to be?
438 or something like that. I'll do that for exams. So I'm going to drop, pardon me. .438 fall exam.
Yes.
2 here. Exam 3 here. Upload stuff, okay. And then I'm gonna go to my C drive, if I can remember how to get to my C drive, because I'm an old man. There we go. Input C5 models. Just give me the freaking file. There we go. And then that C5 models is going to be, the file location is going to be different because it depends on where you install it. I am as lazy as I can possibly be and just put it in my root directory so that I didn't have to type out a bunch of stuff because it's a text file. So it doesn't occupy a particularly large or really any space. All right, so let me resize my windows here a smidge.
Did you make that visible?
Make what visible?
Yeah, it's the
You may have to refresh. Everything is just in the,
exams.
yeah, I just dumped it all in the exams because that's part of your exam.
Yeah.
All right, so I'm going to rename this library and call it ELEN 438 _ fall 2022, because that's what this class is and when it is. And the first thing that we're going to do is play around with some simple circuits in order to figure out what our parameters for our MOSFETs are. So I'm going to call this first one NMOS _ parameters. And double click on this, and I'm going to go to components. And now I'm going to put an NMOS transistor here in my field. I'm going to zoom in. And while I have it selected, you can tell it's selected because there's a white box around it, which you guys probably can't see because of the projector. So let's play with the lights a smidge.
Okay, I'm already waiting.
So I'm pretty
I
sure.
got the thing downloaded.
I'm pretty sure if you went over here, right click on the library, create new cell,
Yeah.
schematic, named it NMOS parameters,
Okay.
and then went into component view, pulled out the NMOS, just put it.
Tell me to slow down if I need to slow down, by the way.
Okay, created a thing in those parameters.
Yep. And then right here, I chose an NMOS and put it in. And so if you click on this little arrow, it pulls up the drop-down menu of all the different things. So NMOS and PMOS are 3-terminal enhancement mode MOSFETs. NMOS and PMOS-D are 3-terminal depletion mode MOSFETs. I'm not sure what all this other junk is. I don't care. I've never had to use it, so I don't give a shit about it.
I'm good.
All right. I'm deleting that one because I don't actually need it. So anyway, while I have this thing selected, if I press Control-I, it brings up the menu. And so for a C5 process, the minimum dimension is 10 in the width and 2 in the length. So I'm making this as small as possible. Pressing OK. While this is still selected, I'm now going to go to Tools, Simulation, and I am going to set my SPICE model. And so that just brings up literally a text block that I'm going to need to edit. So that was Tools, Simulation, SPICE, and then Set SPICE Model. And I have to do that while I have my transistor selected, so encompassed in a white box.
Nothing popped up.
So let me see what you got. So the fact that the word spice model is there means you've done it right. We're about to edit it. Okay. So now, so I'm not sure how well you all can see this, but right now the transistor itself has a white box around it, meaning that it is currently selected. And the words spice model have a light blue X through it. So the light blue thing means that it's not currently selected. Because we're going to have things on top of things and all that kind of stuff, if you press Control while you left click on it, it cycles through the different things that you could select underneath that mouse click. So since there's only two things here, this is just going to swap back and forth between transistor and the editable spice model thing.
It's like it's clicking through the layers.
Exactly right, yeah.
Is there any reason you couldn't click on the spice model and kind of move it so you don't have to?
Well, that is literally, we have to be able to select it first, and to select it, you need to cycle through it to select it. Now that it is selected, we are moving it out of the damn way. Yes. We're going to press Control I with spice model selected. And we are literally going to type in NMOS because our C5 models only has a model for an NMOS transistor and a PMOS transistor. So all of our NMOSs need to have the model NMOS. All of our PMOSs, when we get to that, need to have the model PMOS. All right, so now what I'm going to do.
It's not letting me forget.
Click apply. Okay.
There's nothing. Type in NMOS. PMOS. When in doubt, try again.
Yep. I just have the magic touch. I don't know. All right, so now I have selected ground, which is over on this left-hand menu, and it looks like a ground symbol. And I'm just going to drag it over here where I need it. And it's really hard to see on this screen, but there is a little white plus mark that effectively gives you a terminal. So with this selected, what it's going to do is if we right click somewhere else, so let's say we right clicked over here, it's just going to make a wire from that terminal to wherever we click. That wire right there is to nothing and is obviously utterly useless. So I'm going to delete it, and I'm going to connect my ground terminal to the drain terminal, excuse me, the source terminal of my transistor. And actually, while I'm at it, I am going to just click the plus sign that is at the gate of my transistor, and then right click out here somewhere to the left to give me a little stub of wire effectively for my gate. And I'm going to click the plus sign that's associated with the drain of my transistor, and then right click somewhere above that. And that's going to be effectively my drain terminal. Okay. On my schematics, I don't really do this very often, but we can also put annotation text. So right here, if I put annotation text in, and that was under the miscellaneous file, and press Control I can just label this as the drain so that I remember what's what. And to be clear, I'm getting to that menu so quickly by pressing Control I with something selected. All right, so now this is effectively the circuit that we are going to be quote unquote analyzing or simulating to figure out what the different parameters for our NMOS transistors are. So with this gate node selected, and to be clear here, I'm mousing over the very end of this wire until I get a little targeting reticule, and then I'm clicking. And so it fills it in with a white dot. So when I have that selected, if I press Control E, that is the export function. And so that's how I'm going to export things to LT Spice. So this is going to be my gate source voltage. So I'm going to call this VGS. And then I'm going to press OK. And I'm going to select this text and move it out to the side. It is still associated with that particular node. Now I'm going to click this little nodule on my drain node, press Control E, and I'm going to type VDS. So the simulation that we are going to run here is a DC parameter sweep. So we are going to be changing the value of the voltage source that's connected to our gate node and the value of the voltage source that's connected to our drain node in order to get our relationship between our drain current and those two quantities as we sweep them through different values. So now I'm going to get into my SPICE text. And so I go under miscellaneous and put this SPICE code thing. And I'm just going to drop this over on the left-hand side and then press Control I. This is going to be multi-line text because I'm going to give it all of the commands in one go. So I need to check the multi-line text box up top. So the first thing that I'm going to do is I'm going to declare that my export VDS is a voltage source labeled VDS, and it will be between node 0 or ground. It is a DC source, and it will have a value of 5 volts. It's not actually going to have a value of 5 volts. We're going to sweep it, but we have to tell LT Spice that it's a DC source in order for us to do the DC parameter sweep. And so that's just kind of my default thing. So the export VDS is a voltage source labeled VDS that is 0 on the negative polarity side, 5 on the positive polarity side, and the DC there in the middle tells LT Spice that it's a DC source that I'm putting there. I'm going to do the same thing for VGS. So VGS space 0 DC 5. So now I'm saying I have 2 DC voltage sources connected to my export nodes of VGS and VDS. Now I'm going to do .DC. So that's telling me what type of simulation I'm running. I'm going to sweep VDS from 0.0 to 5.0 in 0.05 volt increments. I am also going to sweep VGS from 0.0 to, let's say, 3.0. That's 30, so that's not what I want. And let's do this in 0.1 volt increments. And we're going to play around with these things in a little bit. Because effectively, why I'm sweeping VGS is because I want to see when the model says this thing actually turns on versus just relying on the data sheet to tell me it's this. The next thing that I'm going to do is .include. And then for my particular computer, since I have the C5 models stored in my root directory, that's where I'm looking for it. So C5 underscore models.txt. And I'll hit apply and then OK. And I'll try to run the simulation and we'll find out whether or not I remembered how to do all of this correctly. So to run our simulation, we go under Tools, select Spice, and hit Write Spice Deck. And now it kicks me out to LT Spice because I have these two programs effectively linked. And I get a blank thing. I'm going to tell it that I want to look at ID, which is my drain current, for my transistor that is labeled M NMOS at 0, which is what the default label was for my first NMOS transistor. And I'm going to click OK. And I get all these nice pretty curves. So what this is my drain current as a function of VDS for the different values of VGS as we sweep it. So this guy right here, this topmost thing, is when VGS is equal to its maximum value, and then one step lower, lower, etc. Right? So let me pop back over here to electric. So since I swept from 0 volts to 3 volts in 0.1 volt increments, this one is corresponding to VGS is 3, 2.9, 2.8, 2.7, 2.6, 2.5, 2.4, 2.3, 2.2, 2.1, 2.0, 1.9, 0.8, 0.7, 0.6, 0.5, 0.4, 0.3, 0.2, 0.1, 1 volt. So what I'm looking at here is effectively I'm trying to figure out under what voltage range my transistor turns on. The scale here is telling me that if I were to change my VGS sweep from 0 volts to 1 volt, I'd get a better idea, because right now everything's way higher than I'm seeing. It's hard for me to see exactly where it turns on. I was just trying to get a feel for where that's happening by having a sweep of this range.
How did you run the spice? I got the spice text from the.
Okay, so no, not a problem. So if we go to tools and simulation spice and tell it to write a spice deck, if you have it set up, it'll kick everything out to spice. So I'm going to delete this, or I'm going to close down this whole iteration of LT spice here, and I'm going to change my VGS thing. Now it's going to go to 1 volt, and let's do it in 50 millivolt increments so we can get a better idea of when this guy turns on. And our vertical scale should not be all the way up to 600 microamps anymore, because we don't have very large values of VGS.
A quick question on the VGS labels. Did you specify the characteristics on that when you press, you were typing out? Because mine was set to default unknown. I might have missed a step there.
So I'm specifying the voltage sources here in this text. So the first thing is the export. So VDS. So effectively at node VDS on this graph, that's where this first label comes from. The second thing is what I'm labeling my voltage source as. So I just use VDS twice so that it's VDS in this simulation or in electric, and it's also labeled as VDS in LT spice. The DC thing there says that it's a DC source. So 0 DC 5 means there's a 0 voltage or ground on the negative polarity terminal. 5 is on the positive polarity terminal, and it's a DC source between those 2 points, effectively. And then I did the same thing for the voltage source VGS. This third line of code is me telling it what to sweep it through. So I'm starting at 0 volts, ending at 5 volts, and I'm doing it in 50 millivolt increments for VDS. For VGS, I'm starting at 0, ending at 1, and I'm now doing it in 50 millivolt increments. So I get a better idea of what my actual threshold voltage is. Did that answer the question at all, or no?
I think that answered it, but really what I was just asking is, since you've got your spice code right there, the VDS, VGS, you're not labeling those as anything different. It's just, this is the spice label for it. Here's what it actually is in the spice.
Yeah, so I'm not drawing a voltage source or anything like that. I'm telling it there's a voltage source between these 2 points, and this is what it's doing.
Okay. I think that answered it.
All right, so I'm gonna run this again. I'm gonna look at my drain current again. And now we have arguably more reasonable things, right? So this topmost curve corresponds to VGS is equal to 1 volt. This would be 0.95, 0.90, 0.85, 0.80. And then down here, this would be 0.75. And then the one directly below that is 0.70. So our threshold voltage is somewhere between 0.70 and 0.75 by my inspection here. Effectively, we're not getting any output current on this thing, or any really reasonable amount of output current on this thing until we're somewhere within that range, right? And I'm just literally counting down. I know that the highest value is 1, 0.95, 0.90, 0.198, 0.75 here. Yeah. So that's what I'm going to say our threshold voltage is. It's about 0.75 volts. Okay. And that's because I'm observing that my device starts passing some non-negligible amount of current, which looks to be less than 1 microamp, but it's not 0 microamps.
We're talking about the like the bluish teal color.
Right. So effectively, if my device is off, if my VGS is below VTH or, you know, less than or exactly equal to VTH, my current is going to be 0 regardless of what my value of VDS is. So the first value of the first current plot that I have that is not 0 across the entire range of VDS values corresponds to VGS equal to 0.75 volts. So that's what I'm going to estimate my threshold voltage to be. We could iterate this over and over and over again if we wanted to get smaller and smaller ranges, but it's really not worth the trouble. This is going to be good enough for government work. We're going to call it 0.75 volts for VTHN. And so actually, I'm going to write that down over here so that we'll know what it is. So VTHN is approximately 0.75 volts, which isn't wildly off of what our C5 models thing tells us. It had a VTH not I think 0.69 volts. So we're off by tens of millivolts or whatever. So not a huge thing, 50 millivolts or something like that. Not going to make a huge impact. All right. So that's our first parameter that we have extracted from our whatchamacallit model here.
Yeah, they use 0.67.
Yeah. All right, so we have plots here. We need to figure out what mu n C ox is, and we don't care about what it is individually. That as a whole quantity is needed because that's one of our parameters that's going to be constant for all NMOS devices. And we also need to figure out what lambda is. So who has thoughts about how we might do that? So for you guys who are on Zoom, you should be here in person. So our drain current for our device is 1/2 mu n C ox W over L times VGS minus VTHN quantity squared times 1 plus lambda VDS. And here's one thing I guess that I'm going to put here. So some textbooks, instead of calling this strictly VDS, they have it listed as VDS minus VDSAT, which is really the same as VDS minus VGS minus VTH. So effectively, channel length modulation should not occur unless we are in the saturation region where VDS is greater than the quantity VGS minus VTH, is what this is really meaning. So I tend to look at this guy right here to figure out what lambda is. So let me put out here for VDS is greater than or equal to VGS minus VTH, and in this case. All right, so if we want to figure out what the quantity mu(n) times Cox is, where again, we don't actually need to know what they are individually, we just need to know what that thing is as a whole. How do you think we might figure that out?
Well, there's a couple parameters we know, like.
Exactly right. There's a couple of parameters that we know. These are our drain currents, right? So this is what this is mathematically describing. We need, for our device to be operating in saturation, we need to know, let's talk about the specific edge of saturation, right? So the transition point between saturation and triode occurs exactly when VDS is equal to VGS minus VTH. Since we know what VTH is and we have control over VGS, we can effectively look at these curves for a particular point where VDS is exactly equal to VGS minus VTH. And then if we know what the current is at that exact point, this part over here goes to 0. The only unknown quantity we have is mu(n) times Cox, because we defined what W over L was. Does that make sense? So let's look at this topmost curve, right? So in this topmost curve, we know that VGS is equal to 1. Get my calculator out here. So VGS is equal to 1. So VGS minus VTH is 250 millivolts. Right? So that means we need VDS minus VGS minus VTH to equal 250 millivolts as well when we're looking at the edge of saturation, right? Because VDS needs to be equal to VGS minus VTH. So at 250 millivolts, let me see if I can click on here. So the problem that I am having right here is that it's selecting the data from the effectively the off states. And I can tell that because my corresponding Y value is 1.85 picoamperes and my scale here is effectively in microamp. So I know that I'm not getting the data that I want. So I'm going to close this again, now that we know what VTH is, and I'm going to edit my command. So we're going to force VGS to be 1 volt, and we're no longer going to sweep it. So I'm just going to delete all of this text right here that was involved in sweeping it from 0 to 1. And if I run this simulation, now I'm going to get a single curve on my graph. I hate how I have to keep moving this stupid zoom thing over and over and over again. I'm going to write my spice deck. Add trace ID for MNMOS. There we go. So we have a single curve. If I click on that, now I can move this guy around, and we're looking for the current when the X value is 0.25 volts. I thought it would just let me type it in, but of course it won't, because that would make my life too easy. So we just have to slide this dumb thing over.
Almost 11 microamps, around 10.96.
So on my simulation, I'm getting 12.2 microamps for a VDS value of 250.67 millivolts.
If you click on the line and use your arrow keys, I think it rounds. So you
Yeah.
can, like, yeah, so click on it like how you have it there. And then use your arrow key.
Oh, I'll be done. All right, so I'm getting 12.2. That's awesome. I did not know that. Thank you. So if we know that, let's do this on the other board here. So we have 12.2 microamps is equal to 1/2. I'm going to call this KPN, where this is just mu n times Cox. I'm just giving it a single variable thing. VGS was 1 volt minus VTHN, which was 0.75 volts squared. And then my channel length modulation thing is just 1 because we're at the edge of saturation. So we're not at the point where we have that linear increase. I'm just solving for KP now, right? So KPN is going to be 2 times 12.2 microamps divided by 0.25 volts quantity squared. So I'm liking where these units are going because my expectation for mu n Cox should be that it's in units of microamps per volt squared. So 2 times 12.2 over 0.25 quantity squared, 390.4 microamps per volt squared. Let's call it 400 microamps per volt squared so that we have a nice roundish number to deal with. Again, we're just approximating things. All right. So let's put that on our table over here. Mu n Cox is approximately equal to 400 microamps per volt squared. Now we need to figure out what lambda is. So we just choose some point at which channel length modulation is a thing. We know what VGS is, we know what VTH is, we know what mu n Cox is, we know what W over L is. The only thing we don't know is lambda. Okay.
Professor, I noticed, because I'm getting a slightly different value than you, it looks like mine is calling it NMOS 1, and it's saying that its NMOS length is 0.4 and width 2. I'm not sure.
Okay, so go into electric. Go into your preferences, which I think is that screw and wrench icon. And go to technology, scale. So that should be 300 nanometers, not 1,000 nanometers for our thing, and press apply. Sure, we're not going to do anything and anything else. All right, and now rerun it and see what happens. And while we're at it, I'm going to double check my scale length because I have a tendency to play around with crap.
I have the same numbers. I mean, still check.
So if I go here to this menu, and then I click on technology and scale. So MOS, fly, okay. So actually that's now I need to see what technology node I had selected, but I feel like it was that one. I have to remember how to do that because it's been a year. But effectively, let me get all this crap out of the way. Technology, submicron, second poly, analog, Mock Moss, yeah. So this is where, sorry, Stephen, I told you poorly. So because we're using the Mock Moss, or I have mine set for Mock Moss, that is why I have a 300 nanometer scale length, which is what the C5 technology uses. So your settings should look something like this in the technology node. We have three metal layers, because that's the three metal layers that we have access to in the C5 process. We're using sub-micron rules. Second polysilicon layer is checked, and analog is also checked, which means we get to choose resistors and capacitors out of a menu as opposed to building them ourselves, which is what I made you guys do for your other thing, because that's just tedious.
I mean, that's what like behind the scenes.
Yeah. So there we go. So apply, okay. And hopefully now you'll get the same-ish numbers as I. All right, so let's put some math back on the board. So can I erase this simple math that we did to figure out what mu NCOX was? Everybody's okay with the minor level of algebra that was required?
My system's still defaulting to like 0.4 and with 2.
Right.
I did. Simulation, splice, specific changes that we made. It's still defaulting to 0.4 after making the adjustments.
So 0.4 microns. So it's doing 200 nanometers instead of 300 nanometers.
Go to technology instead of the way you did it. Let's see. Scale. We're using Moss.
Yeah.
There. So it's set to 200 for some reason.
Okay, so 200 is the default, but I set mine to 300 because we're using a 300. So that's on me.
All right.
Sorry about that.
No worries.
All right, so we are going to find an ID value in a moment. We're just going to pull that off of our graph. This is going to be equal to 1/2 400 microamps per volt squared times VGS, which is 1 volt, minus VTHN, which is 0.75 volts squared, times 1 plus lambda, which is what we're looking for. And then this is going to be VDS, which we're going to choose a particular value of VDS to get this, minus 1.0 minus 0.75. Close parentheses there. So I am going to be lazy-ish and just bring this guy over to, let's call it 2 volts. So VDS is equal to 2 volts. ID is equal to 18.5 microamps. And now it's math time again. So let's do some math. So twice 18.5 microamps over 400 microamps per volt squared times 0.25 volts squared is equal to 1 plus lambda. So 2 minus 1 is 1 minus 0.75. So this looks like 0.25 volts, I believe. And then we're solving for lambda. So I'm going to be lazy and use my numerical solver. So let's see here, the microamps is going to cancel the microamps, the per volt squared is going to cancel the volt squared, so I don't need to do any unit conversions or anything like that. So 2 times 18.5 over 400 times 0.25. And actually, sorry, squared outside here, because I'm doing that guy right there. So I want to make sure I do that right, is equal to 1 plus 0.25x. Solve for x. .92 per volt. That seems,
That's not a lot, right?
yeah, that's real large. I'm expecting like 0.1-ish.
I did the same thing using, you just subtract 1 from both sides, divide the result by 0.25 volts, and I get the same thing without using the solvers. So it's not the solver.
So let me look at what happens if we use the absolute value of VDS as opposed to VGS minus VGS minus VTH. I think that might be the issue here. So that would just be 1 plus 2x, which should scale this down. That means that makes it way more reasonable. All right. So we're going to call this just VDS here. Math, in my opinion, bears it out. So if we put 2 volts here, this stupid marker worked. Just a second. I find that lambda is about 0.25 per volt, which is way more reasonable than 2. That would mean we'd have a really, really steep effect with channel length modulation. All right. So these are our NMOS parameters for our design. What we should probably do, just to make sure we're not tailed out of school here, is I'm going to change the value of VGS to, let's just say 1.5 volts. And then I'm going to use these parameters to predict what I believe my drain current should be at a couple of different values of VDS, and make sure that the parameters that are going into my model loosely agree with what we're getting from the simulation. Again, this is all, we're looking at just things for the ballparkish range here, right? So I'm going to close this out, edit my SPICE code, and I'm going to change VGS to be 1.5 volt. And then rerun my simulation. Looking for my drain current. There we go. All right, so we know VGS is 1.5 volts. So let's say we're looking for VDS is equal to 1 volt. So VDS equal to 1 volt. Is that greater than VGS minus VTH? VGS here is 1.5 volts. VTH is 0.75 volts. So VGS minus VTH is 0.75 volts. If VDS is greater than that, then we are in the saturation region, which is where we're trying to see whether or not our model makes any damn sense, because we want all of our transistors to be biased there. So I think that's a reasonable point, okay? So our drain current ID should be 0.5 times 400 microamps per volt squared. So 400 times 10 to the minus 6 amps per volt squared. VGS minus VTH, that's 1.5 minus 0.75 quantity squared. Multiply that by 1 plus 0.25 times our absolute value of VDS, which is 1 volt. And so I get 140 microamps when VDS is 1. We're getting somewhere in the ballpark of 110. So not super accurate, but we did overestimate a couple of things, right? So we said that mu n was 400 when we measured it to be around 390. We said that lambda was 0.25 when it was actually closer to 0.24. We're just trying to get nice round numbers. We might have also overestimated VTHN as well a little bit since we didn't go through that iteratively. So this seems like it's off a lot, but I would argue that it's probably pretty reasonable. Let me see what happens if I put in exactly 390 and exactly 0.24 and just see if we get any closer. $136 micro, so still a bit off, but I think it'll be okay for what we were doing. All right. Just because I don't want to spend an entire day just figuring out what the most best NMOS parameters we could possibly get are when it's not really worth our time because we're just guesstimating things here to begin with. All right. So we have a reasonable approximation of our NMOS parameters. What I would like for you guys to do is now figure out how to measure your PMOS parameters. I would suggest making a brand new cell, call it PMOS parameters. And then effectively make a similar test circuit. Just recall that for the PMOS device, you want your source to be at the highest potential. Since this is we're designing to a 5-volt supply rail thing, I would say that your source should be at a VDD value of 5 volts. You're going to vary VSG. You're going to vary VSD. And you might want to vary them in the opposite direction as you're used to in order to make the current look positive. So start with a higher value and go to a lower value. Oh, I don't know what I just did. I just want to see if this is doing what I expect it to. Yeah, okay. I'll bring back my electric so you guys can see what I did. So if you have the transistor selected, go to Tools, Simulation, Spice, and then move down to Set Spice Model. So I'm going to pull up LT Spice here. So this corresponds to VSG is equal to 3 volts, 3.1, 3.2, 3.3, 3.4, 3.5, 3.6, 3.7, 3.8, 3.9, 4.0. So it looks like it's somewhere in the ballpark of between an absolute value of 0.5 to 1.5. So this is PMOS hurts my brain to think about because we have to do everything backwards. So let's sweep this from 4.5 to 3.5 to get a better idea. And let's do this in 50 millivolt increments. So 3.5, 3.55, 3.6, 3.7, 3.8, 3.9. So to me, it's somewhere in the ballpark of 0.95 volts, which pretty closely agrees to what our C5 model says, because I think that said it was around 0.9 volts, if I remember correctly. I guess I think I have it open so I can look. 0.92-ish. So it seems like a reasonable approximation. 0.95 volts for VTHP.
When you first ran it before you adjusted numbers, was it like a ton of lines on there?
Yeah, but there's gonna be a ton of lines if I tell it to give me a ton of volts.
Okay,
So-
well, I didn't catch it. To me, I was like, whoa, that looks like way too much, but.
So I had a range where I was adjusting VGS from 5 down to 3 in 0.1 volt increments, which means
Okay.
if all of them had an actual curve, that would have been 21 curves on the right. So here, I'm adjusting it from 4.5 at the lowest to 3.5 at the highest because I have to do this shit backwards because it's PMOS. And so if this is 3.5, this is VGS is 3.55, 3.6, 3.65, 3.7, 3.75, 3.8, 3.85, 3.9, 3.95, 4.0, 4.05, 5 minus 4.05 is where this 0.95 is coming from. Negative 0.95 because we're going to deal with the absolute value anyway, but that's some amount of current. All these other ones look too close to 0 for me. So that's my approximate value. So from here, we can pick a particular value of VSG. So we want it to be at least 4.05 volts, but preferably a little bit lower than that. So we could try something like 3.5 volts, which would give us literally this big curve right here. And then from that, we would try to extract our parameter for mu P Cox. And then once we know what that is at the edge of saturation, we can try to figure out what a reasonable guess is for our lambda P. So lambda N is that. So let's do just that. Somebody give me a value for VSG.
2 volts.
2 volts. This guy's going to be really on. So we're going to make this just a 2 volt source. We're no longer going to sweep it. Close this. Get rid of that. My concern here is that we're not really hitting that linear range particularly well to get anything for our lambda parameter. So let's change that to 3. Right. So there's, I guess, The difference, so the difference between the source and the gate will be 2 volts now if we say that the voltage applied directly to the gate with respect to ground is 3 volts. I guess I may have misinterpreted what you were asking me to do momentarily because of all this backwards thinking. It's hard on my brain.
That's what threw me for all this, and that was-
Yeah. All right, so we do have a nice broad linear range type thing to worry about here. All right, now I got to wrap my head around the math that's going to go into this. So I'm going to write my equation down. So for our transistor, our PMOS transistor, our drain current should be ID is equal to 1/2 mu P Cox W over L. Did we remember to set our size of the transistor? Or did I? Yes, okay. VSG minus the absolute value of VTHP quantity squared times 1 plus lambda VSD. I'm going to throw away this shitty marker. So VSG in this case is the difference between the voltage at our source, which is 5 volts, minus the voltage at our gate, which we've set to be 3 volts. So VSG is 2 volts. This is going to look like 0.95 volts. So we want VDS to be less than or equal to VSG minus the absolute value of VHT or VTHP in order for this guy to be in saturation, because this is a PMOS and everything is backwards and it's driving me insane. Sorry. So for us, sorry, this should be SD. So at the edge of saturation, VSD should be approximately equal to VSG, which is 2 volts minus 0.95 volts is 1.05 volts. But so this is effectively we're talking about right here. So this is where my labeling things is biting me in the butt a little bit, because my source, this is representing what value the drain voltage has, because I'm applying it specifically to the drain. So the source minus this is VSD. So we should be looking for 3.95 volts, the way that I have this graph laid out, because I labeled things awkwardly. That should make sense if we look at the graph. This is where we start to see that it begins to settle towards something. If we were looking at it actually over here at 1.05, we're deeper, 1.05, we're deep into saturation at this point, so that doesn't make any sense. So that's just because I labeled shit oddly. For this PMOS transistor, what we're varying is the voltage applied at the drain and the voltage applied at the gate, while the source is held constant at 5 volts. And so that's why it's wonky-ish looking on my graph here. So I'll think about something that better. So let me move this thing up here to where I can see it. So we're looking for our horizontal value to be 3.95. So 77.5 microamps. Is equal to, do it this way, 77.5 microamps times 2 over W over L, which is 10 by 2. Did we remember to do that last time? Put the aspect ratio in?
I don't have it.
That might be problematic as well. We might have to revisit that. If we forgot to do it, we would actually just divide that by a factor of 5. And so that would be 80.
Oh, yeah, it's not there.
Okay, yeah, so we totally forgot to do that. So that thing needs
That
to be.
explains the CLM being weird.
I honestly don't know if it does because we forgot it every time and it was the same factor of 5 every time. So I don't think that it actually did, but we should update that. So 400 over 5 is 80, right? Room full of engineers,
Yes.
including a jackass with a PhD, and we all forgot our aspect ratio. All right. So we were solving for effectively beta instead of mu NCOx. So it is what it is. We caught it. And then let's see, I need to move this thing over where we found that to be 1.05 volts. Quantity squared is equal to mu P C ox. And I'm going to guess that this should be somewhere in the ballpark of 1/3 to 1/2. It's going to be less than mu NC ox. If it isn't, we've made a mistake. Because the whole mobility is usually significantly lower than electron mobility. $28.118. So this is going to be an egregious rounding thing. So we have a choice to make. We want our PMOS transistors to effectively be integer multiples wider than our NMOS transistors. So we could fudge it and call this 90 and call this 30 so that our PMOS transistor needs to be about 3 times as wide. Or we can leave this at 80 and call this 40 and say our PMOS transistors need to be about twice as wide. Which route do you guys want to go? It's all approximation. We want our numbers to be nice and even so that this plays well. That's really the whole point here. I would hesitate to call this 30 because then we would need to make effectively our transistors channel longer to get our ratios to work out. And we're not making things as small as we could if we go that route. So I'm effectively hell bent on making sure our channel length is 2 lambda, 2 scaling factors. And then from there, it's making the numbers work. So do we want to call this 90 and call this 30? Or do we want to leave this as 80 and call this 40? Just call it 40. All right, rounding it up to approximately 40 microamps per volt squared. I mean, trying to think, I guess technically if it was 30, we could make them 12 by 2s or something like that. So our PMOSs could be a 12x2 base unit instead of a 10x2 base unit. But I'm gonna get forgetful and annoyed. So generally speaking, twice as large. All right. And then lambda P. Let's figure out what happens there. Again, just ballpark and stuff. As long as we're playing the right. All of this is really going to amount to, for the most part for us, is that we're gonna have to play around with the resistor value to get our bias current, what we want to be with our beta multiplier circuit. So we're literally just gonna massage the R value to get our bias reference current that we want. And then from there, it's just, all right, so now that we've established this specific reference current, everything works out. So that's where all of these guesses are going to come to some point of fruition or whatever. All right. So now that we have a value for mu p Cox, so let's see. We know that our drain current ID is 1/2 mu p Cox W over L times VSG minus the absolute value of VTHP quantity squared times 1 plus lambda VSD. So this bit right here, for this math, we're going to call it 30 because that's closer to what it actually was. This is just 5 VS 5 volts minus VG is at 3 volts minus 0.95 volts. Squared times 1 plus lambda, so VSD is going to be 5 volts, and let's say that our drain voltage is at 4 volts, so that we're way out over here. So about 100 microamps. There, all right, so 2 times 100 microamps over 150 microamps per volt squared, where I've just multiplied those two things together. This is 1.05 volts quantity squared is equal to 1 plus lambda times 1. So that should be pretty easy to solve for. Two times 100 over 150 times 1.05 squared minus 1. Lambda is equal to 0.2. Ballpark. Seems reasonable. Oh shit, we're 5 minutes over. All right, so we did fruitful things today. We got to play around with electric. You guys probably learned a little bit more spice code than you did before you walked in the door. All that kind of stuff. We've extracted some parameters, so now we can actually start building things. So my goal for Friday is for us to work on the beta multiplier portion of this circuit, and also the startup portion of the circuit as well. So effectively, every unlabeled transistor on our circuit, handout or whatever, if it's an NMOS, we are going to expect it to be a 10x2. For a PMOS, we're just going to put two 10x2s in parallel to make a 20x2 so that they effectively have the same overall mobility and therefore the same current flowing through them. For some of these guys, like, let me pull it up real quick here. Where is my friggin' file explorer? Oh, it's this weird looking thing. For 38, full exam 3. So for this guy right here, this is listed as a 30x10. Okay, so I want to talk about why it's listed as a 30x10. Who knows what that transistor is doing? So this is this transistor right here that my mouse is near for the 1 or 2 of you who are on Zoom right now, is part of the wide swing current mirror up here. So it has a width of 30 because for the table that's used in the textbook for this, the mobility of holes is 3 times smaller than the mobility of electrons. So the NMOS transistors were made 3 times wider to accommodate for that. The width, or excuse me, the length is 10 because for a wide swing current mirror, we need that extra transistor to have a length of at least 4 times as long. We are going to make it 5 times as long to give us a little bit more wiggle room so that we won't be biased at exactly the edge of saturation, so that when we use it to bias amplifiers and there are slight modulations, we won't push it out of the saturation region. So the minimum size of this, based on what the textbook says, should be 30.8. You make it a little bit longer to give yourself wiggle room, right? Because we want those wide, the transistor that's used to bias the 5th transistor in a wide swing current mirror needs to have a length that is 4 times longer than all of the others. We make it 5 times longer. We ensure the performance that we're looking for. So that's why that one is that long. And we would see the exact same thing. Why doesn't Adobe ever scroll with touchscreen stuff? It annoys the shit out of me. That's the exact same reason this one right here is 10x10. So this one, because it's an NMOS, will be 10x10 in our design, but that 30x10 one will actually look like a 20x10 because of the assumptions that we're making. So just little subtle nuance type things like that. But we're going to be focused, like I said, on the beta multiplier portion, which is just these 7 transistors. That's my goal for Friday. And then once we get that down, we'll start working on this part, and then this part probably the next day. All right, see you guys on Friday. Sorry for running 10 minutes late.